last until 10, 30, 37 degrees outside. That'll be fun.
You would be closer to the parking lot lot of business school. That's a lot closer.
No, the AOS building is closer to the campus. No, it's actually Camp Randall. So like this Camp Randall is the minor.
I had a long night.
No, you're good. I can't wait to hear this. Tell me afterwards.
Okay, good afternoon. Welcome to Weather Watch today. We have a pretty active weather regime, not so much over the continental United States, but out over the Pacific. And perhaps one of the most extreme rain events for California in 20 years is in the forecast for the next, for over the weekend into early next week, with winds along the peaks of some of the Sierra Nevada mountain ranges getting up to 180 miles an hour forecast, and rainfall totals half a foot to maybe even a foot. Snowfall totals several feet. So this is a drought buster for parts of the western part of the United States that we've been talking about have been chronically dry over the last several months. They've been partly a decades-long drought, extended drought, and this is something in the short term they're going to probably make up some ground, but certainly not enough to totally reverse everything. But the impacts of this we'll talk about, particularly for those students in the hazards class. Think about it, it's been dry for so long, there's going to be significant runoff. They've had lots of fires. We'll see what happens, when you get lots of rain on fire, you can get lots of land flow as well as debris flow, including mudslides, trees, the trees that have been weakly rooted are going to come down. All that vegetation that used to slop up the water is not going to be able to do it. So we'll get into those impacts, but let's first focus on the weather closer to home over the upper Midwest. So here's the visible satellite image from this morning and up through just recently. And you can see the broad, extensive clouds and low clouds that are located over the Ohio Valley into the parts of the Midwest. Looked like we were going to clear out last night. We got into a brief period where it cleared out. Lows this morning at 2:53 this morning. We dropped below freezing for the first time. Our growing season is now ended. The earliest time that we've gone below freezing was on, this is provided by Ed Hopkins, was September 12th in 1955. Latest November 3rd in 1943. The median day for our first frost, is on the 6th of October. So we're a little bit behind in that. We've had a warm season. But yeah, our growing season has, I guess, officially ended with our first frost this morning here in Madison. We have clear skies that moved out. We have some low clouds that have moved in, and we'll see on the radar some light precipitation in northwestern Iowa as a weak short wavelength disturbance and a northwesterly flow comes by us. This has been tracking along pretty quickly, and we'll go through later on today and this evening. Elsewhere across the country, one thing you'll note from past weather watches this time of year, earlier this the season, we look to the southeast or parts of Florida, we'll see as the sun comes up, we'll see lots of speckled clouds beginning to come up and small cumulus clouds. You can see that over parts of the Florida Peninsula, but it's less evident today. And that's probably, as we'll see when we look at the surface map, due to the growing season beginning to come to an end, but also the ground's a little bit drier. The air mass is down here a little bit drier, so the ability to get air rising, lifting, forming these convective clouds, even if it's just fair weather cumulus, is going to be a little bit tougher to do with a drier boundary layer. You can see some parts of the Mississippi River Valley show up nicely with a difference in soil structure along that. It's really just an interesting satellite image. Again, when we look to the radar, we'll see that it's pretty uninteresting. Let's go west a little bit, please, Pete. And over the western part of the United States, you can see one of the last vestiges of an atmospheric river event that impacted the west coast of the United States. We'll look at atmospheric rivers in just a bit, with this strong southwesterly flow ahead of a very deep upper trough. That produced some rainfall. It's still raining in parts of California, Oregon, and Washington State, and that rain is going to eventually abate as this weather system moves further to the east. but a more significant weather system is just on its heels out over the central Pacific. There's not much more that I want to say about this particular image. And of course, if there are questions, please chime in. Let's now go to the radar, please. So we'll look at the composite radar of the United States, just a short loop. It's just to get the thing speed. Okay, so there's that rainfall I was talking about in northwestern Iowa. We'll kind of look at the origins of, can we identify a forcing mechanism for this light rain. When we look at the surface objects, you'll see the dew point depressions aren't too bad, but this is really just some light rain. Maybe it's falling between some stations. A few showers along the Florida Peninsula and just off the mid-Atlantic coast of the United States. And then there's that band of rain associated with this decaying atmospheric river structure moving from California just south of the Bay Area, from Monterey all the way up into the Sierras, producing rain and perhaps snow at higher elevations associated with this. And some showery precipitation. We know in the west coast of the United States, typically after the passage of a front, that's when we see some of the deepest instabilities. There's a fairly significant upper trough that's just to their west. And so underneath that upper trough, that PV anomaly that's in upper levels, the stratification is weaker, and ultimately you'll get showery type precipitation following the passage of the front. So that's what's occurring right there now. But again, any rainfall for them, particularly if it comes in a light fashion for a persistent period of time, is going to be good for just about any part of the western United States. Let's now go to the surface map, please. Check out the current weather here in Madison. First. So we recovered nicely from our low of at least 31 degrees, and dew points pop back up. We're at 44 over 37.
Assuming like I normally expect.
Yeah, 44 over 37, mostly cloudy skies, a light northeast wind here in Madison, but nice visibility. You can see some of these places just north of Storm Lake, Iowa, 38 over 34 with light rain, kind of a chilly rain. No one likes rain when it's in the low 30s. Probably prefer snow, but some people don't even prefer snow at that temperature, or any temperature for that matter. But anyway, light rain in northwestern Iowa. Again, the dew point depressions aren't too significant. I don't think it's a lack necessarily of significant water vapor, but just the forcing isn't particularly strong for this particular event. I'm not a big fan of these analyses with the fronts on, but there they are. These are sort of automated, I guess, from the weather service. So the southeastern United States, yeah, dew points aren't too shabby, but they're in the low to mid 50s, and parts of northern Mississippi and Alabama. And then you get further to the south, the air gets a little bit juicier in the 60s, the upper 60s in fact, which is a little bit surprising. I guess the sun is still coming up. These are shorter, but again, we did too much in the way of cumulus clouds. When you get over to Florida, with dew points in the 70s, that's where we saw a few more cumulus clouds that were forming, and it's certainly warmer there as well. Temperatures in the 80s, so you get this convection occurring, forming those cumulus clouds. Let's go back to the western United States and see what's happening in the odds out there. Okay, that front shows up pretty well to the extent you want to trust the analysis that's on this. Nice wind shift, fairly modest pressure trough associated with it. And there are these stations that are reporting in central Oregon, light rain 48 over 44, southern Oregon moderate rain 41 over 39. As you can see, there's 46 over 43 with light rain. Don't know all the names of these stations, there are many of them. San Francisco 58 over 52. And a few light rain and rain showers occurring out over the Pacific coast of Oregon and Washington State at this time. So still southerly winds out ahead of it. And that wind shift is kind of obvious here, but the winds turn back to the east as you go further behind the front. Okay, so let's go to the upper image. John.
Hey.
Welcome, welcome, welcome. All right.
No one, cheers.
So we're going to talk about something today, John, that beats tropical cyclones.
I anticipated that's why I'm here.
Excellent, excellent. All right, let's first start at 250 hectopascal. This is the 250 hectopascal map. You can see modest jet streak that's flowing by us with a northwesterly flow. You can see a nice, there's a maximum temperature right here, so we're probably just above maximum potential vorticity that's located a little bit further down. You can see the height contours have a little kink to them here. It's actually an indication of another wave further upstream. But the most conspicuous feature on this map is this roaring jet out over the Pacific. Okay? And this very sharp upper trough that we see just along the west coast. As I mentioned, we could see in the satellite imagery sort of the evidence of some convection. We saw some of the well, you look at the satellite image, we look at these radar cameras, we could see some showery showers that were located just off the west coast of the United States as this upper trough was beginning to move onshore. Really unstable, really cold beneath this upper trough. And there it's located here at 200 hectopascals. You go 250 hectopascals. You go further back over the Pacific again, there's an extensive jet, and we're going to be dissecting this, slicing it up a little bit later on. But I don't want to focus on that feature too much at this point. But the other thing that I think is kind of neat, we'll go down to 500 hectopascal, is, in my mind, kind of a lack of significant baroclinicity, that is horizontal temperature contrast, at 500 millibars here now in the late parts of October. I mean, there is a pretty impressive upper, modest mid-tropospheric front that shows up here over the Dakotas. And that's associated with that trough that we saw at 200 hectopascal. But really, and particularly if you looked at the map from 0Z today, just early, 12 hours earlier, this baroclinicity was way up here in Alberta. This is a pretty flat map, and I don't know if John or Greg want to comment on that. This is not a typical map you would see this time of year over the continental United States.
Yeah, I agree. Greg started the stream this morning with a couple of texts about that. It made me think maybe it's worth just kind of investigating the intensity of 500 millibar temperature contrast at 30-degree longitude segments and seeing if this is consistently the case somewhere at this time of year. I don't know.
Right.
Really curious.
I was thinking of doing something similar to what John is saying, and to investigate how odd this is.
Yeah.
And I think globally, looking at it, the southern hemisphere polar night jet is still very, very strong, with subtropical jets entering it. And I'm not sure if that's normal. I think the southern hemisphere should be raining down a lot more than it is. And at the same time, the northern hemisphere should be spinning up. And as I mentioned last week, we're seeing the beginnings of the polar night jet, and indeed it is there now.
Right.
But still not very strong for this time of year. And I don't know, is that normal? I'm going to go back and get a series of maps at this time of year and try to compare to see how normal that is. But I get the impression that the tropics are full of energy. They want to complete a circulation in the exotropics, and because of lack of baroclinicity, I get the feeling it's hard for them to do. There's a very low index pattern right now globally. Not a lot of amplitude in the waves, and almost zonal all the way around.
Right.
Not in the Western Hemisphere. Look at that map. I mean, that's the thing that catches my eye too. It's too big.
No, there's this one little trough here right off the coast of North America.
Is that right, this one?
No, the one on the west.
Oh,
on the
West Coast, yeah.
This map is very misleading because if you look at the latitude lines, they go around almost in a circle because of polar starographic projection. But if you look at a Mercator projection, where you just get latitude spread out, the jets, like I said on the text, the jet stream from the west coast is almost continuous all the way around to Libya, mostly zonal. There's a little bit of oscillation there, but it's mostly zonal, all the way back to Libya across the
We
Pacific.
could bring that up from Pete's page. We can look at the stereographic analysis, or maybe the sixth analysis from the GFS from this morning, 12Z this morning. What do you want to look at? That's your forecast maps, GFS polar stereographic projection. Top down view, 200 millibars or 300 millibars at 0. see up there. Let's try the 60 run.
It is a 60 run. Well, something's not right.
Okay, well, we can
Look at Greg's shape page with the numbers coming back.
Just get the 6Z, but only the first frame, because half of them are missing again because of the data problem.
We've been losing so much data from inset recently.
Just get the first frame.
Yeah. So as Greg was pointing out, from Libya, across Egypt and just north of Saudi Arabia, all the way around the globe, so just off the west coast of the United States, you have a really strong.
You can
very
see there's
evident
some
tropical
ridging
jet.
over the Pacific, but not very high amplitude. You figure that goes up, really up to the Alaska at many times. So it's almost like it's zonal. I mean, it's slightly progressing poleward, but, and then the polar jets are pretty pathetic. And you can see the polar night jet has appeared.
Right in here.
Yeah, and the easterly flow, I'm only doing westerly flow here, but the easterly flow is in the rest of the hemisphere, so it's kind of shifted over, I think it's shifted over the Siberia a little bit. It's not centered perfectly on the pole, but that's fine. But look at that southern polar night jet.
Still roaring along.
We're getting late into their spring now. And it's really strong down there, and we know that this year, there's a very strong ozone hole. It's been decreasing over the past, couple decades, as we backed off on hydrofluorocarbons.
Right.
But now, this year, for some reason, the ozone hole is strong again. And so in the Antarctic has had a record cold year, for whatever reason. So the Hadley cell that favors the southern hemisphere has still not wound all the way down, as you can see with all those subtropical jets down there. It's a lot less than it was last week, so it is going down. But I think that's a little unusual. There's so much emphasis on southern hemisphere Hadley overturning.
Okay, so an interest, yeah. Brad.
So the ozone hole was not record this year, but it's record now for the largest extent at this wave of the season. So it's just, as you're saying, a very persistent polar night jet.
And that's what causes it. I mean, even if the sun comes up, if there's an ozone hole, it's not going to heat it, or begin to heat it and remove the cold temperature anomaly at the high stratospheric levels, which is what drives the polar night jet. So it's not winding down as much as it could. I'm guessing that's because the ozone.
That's interesting. It's a sort of a photochemical effect.
Yeah.
Of the lack of ozone there, so it can't absorb the UV.
Yeah.
And so that leads to maintenance of the strong jet. An interesting index combining the thoughts that you have and what John's been looking at. I'm wondering if you did if you could identify the subtropical jet, or the largest component of subtropical jet in both hemispheres, and calculate the circulation associated with each. So just UW length. And just compare them throughout the course of the year, and just develop a climatology. That might be kind of an interesting
That would be.
calculation, just to see when seasons shift.
And that's what you see flip in the climatological data. It's always shown that the Hadley cell is biased toward the winter hemisphere.
Right.
But to watch it switch and when it switches is interesting. I think. I don't. Of course, we don't know what that means, but in terms of actual weather, but it is a little odd this year.
Right. So
As far as I can tell, I'm not sure.
that's interesting. I'm going to go back to the superpeats for a second and just say a little bit about the precipitation that's over the south, over northwestern Iowa. It wasn't something that, frankly, I would have anticipated. So this is 500 hectopascal. You can see this upper trough. So there's an upper trough here. It's modest. There is a significant amount of baroclinicity. We saw the jet streak associated with this. So there may be a role for some jet streak dynamics that we could use to understand what's happening, particularly as this upper trough, at least early this morning, was located near the exit region of the jet. Let's go down to 850 hectopascal. Baroclinicity, interestingly enough, does increase in considerably once you get down to this level, maybe still not as strong as you might expect. There is a modest amount of warm advection here, but it's not particularly significant on this particular map. You can see there's actually a small strong, that's north flat with a southwest wind right here. But paraconicity is strong, so there is a sort of a frontal type structure that's located here, but this isn't really an active front in terms of frontogenesis going along with it. So we're going to look at some diagnostics from the MM5, and then we're going to begin focusing our attention to what's going on the West Coast. So next, let's just go to the current MM5 run, please, Steve. We'll do our normal thing, and since John's here, I must do this again. John's favorite meteorogram, there you go.
Yep.
Chilly weekend, again, temperatures getting up into the 40s over the course of the weekend. Pretty quiet, at least until we get to Sunday. Relatively low dew points, and then they finally begin to climb up as well as we get into Sunday night, and maybe a little bit of light precipitation as a cyclone begins to develop to our south. Let's go to the time height sections for the same time period. In those time height sections, you can see sort of a double dip, if you will, of the dynamical tropopause, sort of two periods as it goes by us. Again, if we were to look at something in Iowa, it would probably be a little bit more prominent since the trough is probably deepest just to our southwest. But again, it's not particularly strong in terms of the depth of penetration down into the lower troposphere. You can kind of see the orientation, that's partly because of the short wavelength. It doesn't have a great penetration depth. I mean, you can see the isotherms don't get really perturbed once you get down to about 600 millibars or so. So it's pretty stable, I would say, from that. And obviously the boundary layer mixes out as best it can, even with the cloudiness that's over us. And then you can see strong veering of winds with height, assuming it's geostrophic, that's going to be associated with warm advection, and depending on how it's localized, perhaps some strong significant ascent, which we see in the blue contours, which are negative omega, so positive in this sense, being upward, and you can see the relative humidity is increasing with that strong vertical motion. So even in the face of strong vertical motion, we should cool the column, or actually warming because the warm advection is sort of beating that out. So what I'd first like to do is just verify, if we go back a quick feed. Again, the most exciting part of this discussion, I think, is going to be the Pacific, but I want to just talk a little bit about local weather. Let's go to the 6-hour forecast for precipitation. Okay. It's pretty dry here, so that's not, at least here certainly, but also over parts of Iowa. If we go to the 12-hour as well, we'll see that it's probably not much to talk about there, and that's all right. There's a little bit of precip in the lee of the Great Lakes, perhaps, but that's not the big disturbance. We know it's precipitating here. Let's look at, and this model is not forecasting the precip, but let's look at one diagnostic that kind of summarizes the forcing elements from a quasi-surface perspective, which are the Q vectors in this layer. So the 6-hour Q vector. Okay, just to the southwest of the region where we're expecting the precipitation, where we know the precipitation is occurring, we do have a nice area of Q vector convergence. It's pretty modest, okay? Indicates a little bit, since these Q vectors are directed from pole to warm, maybe some very weak frontogenesis. But it's maximized there. If we go to the omega in the model, at the same time, 700 millibars, same time, 6 hours. Not what I was looking at earlier. There is a region of weak ascent that's forecast by the model here as well. So just to be consistent with it, that's where we saw the Q vector convergence in the model. That's where we saw we can see the vertical motions here. This light blue here is sort of weak, perhaps weak ascent, but it's not nothing I would certainly write home about. I never write home to my mom about vertical motion at all anyway, so it doesn't really matter. Let's go back from this and then finally look at the relative humidity at 700. We have relative humidity on this, right? And it's relatively dry here. So the model is diagnosing this area of Q vector convergence over eastern Nebraska, southwestern Iowa. Vertical motion's relatively weak, not much moisture. You're not going to expect precipitation from this. Unless I'm missing something here significantly, and we have an older run to look at, but I don't want to focus on that too much. I was expecting to see, there was a nice coincidence of area of precipitation in the model with vertical motion that may have been from an earlier run, but it does not seem manifest in this. So that's the breaks for me in terms of looking at this, but just want to to demonstrate the coincidence of this or the lack of it. So there's something weird about the model. It doesn't have robust vertical motion. Let's go back a click, please, Pete. And we'll go to the 18-hour forecast for surface precipitation. We see the cold convection continues over us with a very deep cyclone out over the parts of Ontario and southern and over James Bay. We have broad anticyclonic circulation beginning to build in, and the rainfall out of the western part of the United States continues with more, this is showery precipitation moving into the Pacific Northwest. But the weekend here is going to be quiet. Let's go ahead another 12 hours. The 30 hours of the forecast tomorrow at 1 o'clock. Rainfall continues with the westerly flow over the Pacific coast, and then to our south we'll begin to see rain beginning to develop along a warm front. You can see the leading edge of warm advection beginning to, or area of warm advection beginning to form over parts of the area just to our south over Kansas and Oklahoma. But the 540 line, very drizzle of snow. It's not going to snow here, don't worry about it. Just right over some of the colder temperatures we've seen over us this season. Let's go ahead another 48 hours, please. So this is on Sunday morning. And we see in the forecast pretty obvious area of precipitation that's just to our south. Okay, the column's getting moistened. We're seeing strong warm advection, so localized warm advection in this region. If we go to look at the same time, the 500 millibar forecast at 48 hours, we can see well upstream of this area is a pretty vigorous trough, the remnants of that trough that just moved into the western part of the United States. So downstream of it, to the extent that this vorticity is even nearly geostrophic, you might expect to see significant vorticity advection downstream of this upper trough over parts of Kansas and Nebraska, with the warm advection a little bit further to the east. We want to see the vorticity advection increasing with height and the Laplacian warm advection kind of localized for us to infer vertical motion. But we could also use the QG quasi-surfing Q vector at this time and to combine both of those ideas at 48 hours. And you can see, at least for this map, most of the Q vector convergence is back over Nebraska and Kansas at this time. This is a layer average Q vector convergence. There's some modest Q vector convergence to the east of this, where we also saw some of the vertically ascent that was occurring. When you use any of these diagnostics, you have to be careful. Having things that are ready-made and cooked like this, knowing what layer to look at is going to be important. This is just something, it might be opportunistic to find something that works just right when you do it, but you always want to adjust that as necessary. Okay, let's go ahead to 60 hours in the forecast as the rainfall begins just to our south. And that low has emerged from the central plains just south of us over parts of Iowa. Significant area of precipitation. These brown colors are about 1 to 1.5 inches of precip, and pretty significant warm advection downstream of the surface cyclone. A couple of bridge point storms that have developed in the Atlantic and the Gulf, but those are, I think, largely fiction. But this is the big system in town. Western part of the United States and the Sierra Nevadas and Northern California, beginning of their massive rainfall event, which we're going to look at closely in just a moment. Let's go down to, again, persistence. Since we've been talking about Q vectors recently, I want to just try that out for this time period. And here we do get a nice region of Q vector convergence to our south. In a region, when we look at the vertical motion pattern, you can see that shows up pretty well. This is also indicating frontogenesis. A strong component of these Q vectors are directed from cold to warm, so this is indicating largely some frontogenesis to the north. There's kind of these isotherms to our north. But again, this shows up pretty nicely. And if we go to the omega at this time, I imagine we are going to see a nice correspondence between that and the vertical motion. And that's pretty close. Not right on the picture, but there you go. Some of this is going to be modulated by the stratification and things of that sort, which we have included. Okay, so the next thing I want to turn to, I'm going to get this just right, is click on this Nws Product View. Okay, this is a little small. I'll make the text a little bit. So this is from the Weather Service office in Reno, Nevada. They're talking about this phenomenon, so-called significant atmospheric river, still on track for the late weekend into early next week with heavy rain, mountain snow. And they're saying that the European Center guidance, QPF guidance, compared to the 20-year reforecast period, is indicating liquid totals higher than any event in the last 20 years for parts of the Sierra Nevada mountain range. This is a big event. And so they're looking at the possibility for, everything set up for them to get a significant or major precipitation event starting later this weekend. And there are issues about snow level, things of that sort. Obviously, anytime you have precip, it's really great if it can fall in the form of snow up in the mountains and gradually be there as a source of water for long periods of time. You don't want just liquid water that'll rush down and create significant flooding issues and hazards. But this is something that they're actually kind of, they're excited about. So let's take a look at what this system looks like. And to first start off, I have a tropical tidbit feature right here. I want to first go out into the Pacific. I don't want to lose this. We got another one. Sorry, Pete. Go here. Click on this. And we can change the image that we have here to we'll keep this. And let's go to the initial time in the model forecast. We'll go to 6 hours. We'll go to 6 hours. I'm going to step forward first of all. So the feature of interest are these two pairs of cyclones. All right, one that's located at about 170 or so west, and one a little bit further to the northwest, 180 near the date line. And as we step forward in time, every 6 hours, we're going to see these weakening slowly. And we'll talk about that in a second. Okay? At least getting less distinct, I'll say that. And then you'll watch here at the 963, down to 947 in 6 hours. That's pretty decent for a mid-latitude cyclone. John, would you agree?
Yep.
Down to
Good for a
942.
hurricane, I'd say.
Yeah, that'd be even good for a hurricane. 942 down to 941. Really significant storm, 946 there. So if we go back to that beginning of that 6 hour period, I also want to show you where this cyclone is. We'll go to the Japan meteorology page. This is from their satellite imagery. Japan, here. Hopefully this is there. So this is a loop that's about 36 hours long. It ends at around 15Z today. And the feature that becomes our cyclone, make sure I got the right time. This is yesterday at around 18Z, is in this cloud head right here. Actually, it's this cloud head right here. That's actually the one that's responsible for the cyclone. So you get to the end of it. So another feature that's going to be important is the cyclone that's just north of the Aleutian Islands that's deepened considerably here. Okay, so this is a fairly intense cyclone. We'll look back at the weather maps. You'll see what the intensity of this was. But I believe this cyclone is playing a role in kind of squeezing this nascent disturbance that's developing baroclinic wave. This is, if we can stop it at the final frame, we'll just get a sense of where this was this morning. So it's this feature here in the Central Pacific, just south of the Aleutian Islands, that's going to play a big role, I think, in the big storm that's going to emerge later this weekend for the West Coast. Another feature, this is an IR image, infrared image. You can see the speckled nature of these clouds here. This is pretty chilly air that's spilling out over the waters of Bering Sea and crossing the Aleutian Islands into the North Pacific. Really cold air, so that's going to enhance the baroclinicity to the north. But there's going to be broadly a confluent flow in this region, and we have this disturbance entering this confluent flow. It's trying to get organized ahead of the entrance to this confluent flow, but it kind of gets squeezed. And we had a really nice discussion yesterday in our 452 class of the effects of confluence and difluence on developing disturbances and how the vorticity can get stretched out. Either, the notion of vorticity superposition and how you can bring like sign PV anomalies closer together and get a more intense storm. Well, the opposite is also going to be true. If you take like sign anomalies and stretch them out, that's going to lead to a much weaker, less energetic storm. And what I'm thinking is, at least on the initial part of this development of this storm, this very deep storm in the Aleutian Island chain near Alaska is helping to create a largely confluent flow. So this developing baroclinic wave here, and the one to itself, we saw there's kind of two in the maps. They get kind of squeezed together slowly over time, get the deformation kind of squeezes them so they get less dynamically active, more inert. And then they enter a region where the flow is more difluid, and they kind of begin to just burst out and begin developing. So we go back to that tropical tidbits page for a second. Here is this really deep cyclone, 954, this northwest flow, and as you can see, it's pretty evident there is some confluence along this. You'll see this kind of getting shunted southward as these two disturbances move eastward. Let's follow the track of that. Also plotted on here, again, the contours are sea level pressure, and this is an integrated water vapor. This is total precipitable water, and these winds are 850 hectopascals. So we step forward in time. These kind of get close together, and then eventually they begin to, the cyclone deepening begins to occur. Let's go to what they call upper dynamics. Don't like that term, but that's the term they have. Look at 250 millibar winds. We're going to start off at 6 hours. Okay, really impressive jet across the Pacific. We saw that earlier. This is the one that kind of wraps around the globe from Libya to just the west coast of the United States. As we step ahead in time, we can see the cyclone beginning to develop near that jet exit region and significant deepening occurring. And so what I did was I said, first of all, let me just take a cross section through this jet, and it's going to be at the bottom P before we get to this by V. Maybe move that over. This was from the 6C run of the GFS, 24 hours, so it would be valid 6C this evening. And you can sort of see the potential vorticity in the color pattern. The purple contours are lower tropospheric vorticity. That's that vorticity structure that's associated with, well, presumably it's going to be associated with it, well, it is associated with the developing cyclone that we saw at the surface, and also very likely moist processes, PV, that are occurring in that cloud head that we saw on the satellite image. Cross-section from A to B, A to the north, B to the south. And this is just, I think, an extremely impressive upper front that extends all the way from, well, stratosphere down to just about 700 hectopascal. The intense baroclinicity associated with it, you can see the isotropes across it, as well as the strong cyclonic shear associated with this jet. In this cross-section, I think this gets up to about 180 knots. If you take the component of wind normal to the cross-section, I think it's about 240 knots. It's a really impressive jet. And we have this PV that's been subducted from the stratosphere into the troposphere. Again, the dynamical tropopause at 2 PDU surface goes all the way down to 700 millibars. Just an impressive front.
What's the isentrope that goes straight across to that jet?
Which one? This one?
Yeah, the one, yeah, right in the middle, it goes straight across, it would,
Right. Straight across.
well, it goes straight from the north to the south, you know, it's the flat,
The flattest one here.
go up a little bit, the one, it would go through the core, right?
Right, it has to go through the core, right. And so this one is 345.
345?
345, 340.
That's mostly a polar jet type of,
Well, that isotropic level is almost, well, I don't know what late October, but we have data from November 1 to March 31, and that's subtropical, 340 to 355.
oh, that's still subtropical?
Yeah.
So again, really impressive upper front that forms with this. We're going to look at a couple things before we get to some of this 5D, and certainly invite John to make comments or suggest how we might want to slice and dice this, or anyone really to make comments on this. We go back to, let's get this right, lots of interesting things to look at with this particular event. Upper dynamics again. Hope we had a triple pause. My apologies. Go back to lower dynamics. Missing something up here. No, okay, for this. I don't think, let's just click on that, but I don't think that's the one that yeah, this will actually will change. So this is finished vorticity. It's not the dynamic control clause. That's what I used to construct the cross section. And if you go ahead, this is from the 12Z run, so it's going to be very similar. If you go ahead 12 hours, this is close to the time I did the cross section earlier. And you can see this vorticity structure. If you go back a few clicks, please see. One of the things that's really neat is, again, you can see some evidence of confluent flow. This is a strip of lower tropospheric vorticity at this time. As you go step forward in time, it does begin to sort of ball up as the cyclone begins to develop, and you'll also see downstream, this PV begins to get eroded. Downstream of this, probably indicating significant latent heating, and we're getting this other, this is formation of another deep upper trough behind it, an upper front that forms just to the southwest of the cyclone. So if you do a cross-section through this, you're gonna see that, that shows up really well.
Go back a couple of times, I think you can see, right between this time and the next one. So you can see that PV gets a little bit more intense in a local spot. Yeah, and I think that's probably, there's a lot of subduction going on at the front end of that, which is part of the story here. And then I think the latent heat release and the development starts to take over, as you point out.
Right.
That might be, if you ran this thing with no latent heat release, I bet you don't get the record storm.
You need latent heat.
That'd be really interesting. It might still be intense, but I don't think it'd get down to 940s.
Right, and I know has been working on running an empath simulation of this just to get a sense of what that looks like, and maybe we'll show that next week, just to show some other tools that we have in our toolkit. Okay, really intense storm, and again, I want to look at a couple other things while we're here. Go back to, I think it's Fluor Dynamics, we'll find this. Significant wave height, just want to show you some impacts here. This is just amazing. So let's go back to 6 hours first and just sort of step forward. So this is one of the outputs of the GFS, and Couple Tidbits provides us a nice set of maps that shows significant wave height as well as the direction of the swell. And you can see as we go forward in time with this, as this approaches the west coast, this is near the final time of the forecast, looking at wave heights that are approaching about, make sure the units are right, 30 feet or so in height. So pretty significant storm as it hits the west coast of the United States. And that's going to certainly cause erosion of beaches and maybe some property loss in places that where these waves strike. If we go back to, well, not to go back, the other thing that I'd like to point out is another map. This is from a site run by the folks at Scripps. I guess it's Marty Ralph's group that looks at atmospheric rivers. And they have a quantity here which is the integrated vapor transport. So you're taking the winds times the mixing ratio or the humidity, integrating that over the depth of the atmosphere and then producing sort of a composite map. If we go back to let's just go to the beginning of this period, you can sort of see this transport of water vapor toward the west coast of the United States. If we go back to the start of this is this morning, right? This is 60, right, so 60. This is the so-called atmospheric river that made landfall yesterday and produced significant rainfall in parts of California, Oregon, and Washington State. And if we go a step ahead, today we saw that was kind of moving inland and beginning to weaken. There's another atmospheric river that's kind of diverted to the south, not doing much as it approaches the west coast. So then here comes our storm, the really intense storm. And it's basically, as some of the forecasters read some of the forecast discussions, they kind of liken it to a fire hose being directed right at the mountains of the west. And that's going to, with the orography here, that really moisture-rich, moisture-laden air hitting these mountains, the upslope side of these mountains, is going to create significant precipitation. And we'll see what those numbers are going to look like in just a few moments. But a really significant event, again, with this transport. So this is a tool they use to look at the strength of these atmospheric rivers. They come up with a numbering scale for these, and this is considered a 4 in their 1 through 5 scale, which is one that's going to potentially cause significant damage but have some benefit. In this case, because it's been so dry, they expect this is going to be good for some of the basins. There are lakes out in the western part of the United States that are at 25% of capacity, and they're going to certainly love to fill up. And there's the flooding risk in terms of dams overflowing, at least initially, is not going to be a problem at all, because all this will well up into empty reservoirs or nearly empty reservoirs. All right. Next thing I'd like to do with this is, let's go to the Vis5D setup. This is from the 6Z run of the GFS, and we can go to 6 hours into the forecast just to kind of get ourselves oriented. There are a couple interesting things, even at the initial stage, before we get into the model forecast. One is that, this fairly significant trough that shows up.
We want to just orient people, it's a little hard to see.
Yeah, okay, yeah, here's the west coast of the United States and Canada. Here's Alaska, Kamchatka Peninsula, and then Japan over here. And so what we're looking at in the white contours, thanks Pete, that's the purple. The white contours here are sea level pressure isobars. Again, this is valid this morning at 12Z. Okay, you can see, again, a fairly deep upper trough, both at the isosurface of potential vorticity. And if we just tilt this upward, one of the first things you'll see is just a very impressive upper front beaming. Just go over to the bottom of this for a second. Keep tilting just to see the thinness of this. This trench, I think, is absolutely remarkable. I mean, look at that and think, wow, that's an impressive upper trough. The one associated with cyclone to be that's further upstream is nowhere, it doesn't really get anywhere nearly, at least in this forecast, or at least in this depiction, as strong. But the fact that it got down to 700 hectopascal in the cross-section for frontal tidbit suggests maybe that's a higher resolution data set we're looking at. But the feature that's going to be of interest is this sort of innocuous-looking surface cyclone right here. This is the one that was already in the Aleutian Island chain that I contend is going to play some role in initially weakening this disturbance, but almost like a rubber band, you're sort of pulling all the energy into it, and then it releases it as it gets to the exit region of a more confluent flow downstream. So if we step forward in this, we can see the evolution of this tropopause with time.
Right there, it starts to get interesting. See how it gets really sharp a couple of clicks back? One more. Right upstream of that little low, you start to see a deepening, a sharpening. See that?
Mm-hmm.
That thing's coming along before there's any curvature in the flow at all. Or not much anyway.
Yep.
That is a local spot where it's lower.
Yeah, maybe we stop right here and just take a look. Let's just tilt that up a little bit. It's already beginning to come down. So the tropopause is lowering.
Yeah.
That's creating a more localized anomalous value of potential vorticity upstream of this disturbance. And keep clicking. And here it's about to just go. Look at that.
What does that look like underneath?
Yeah, to go tilt back up. We can tilt here. Keep tilting just to get a sense of the structure there. Impressive, but it doesn't look as deep at this point as
Yeah.
the one at the initial time, but I would suspect that we might see a different outcome once it actually develops.
A little more localized, I suppose.
Mm-hmm.
You know, the curl is
yeah,
kind of
yeah.
really local.
So really impressive upper front with this, and you can see the sort of treble clef shape in the structure of the PV itself that John looked at.
Yeah, my quick look this morning at this thing was it doesn't really seem to have a very clear-cut occluded structure in the late stages, which is interesting. I don't know if that's actually true or not. It was a very quick look.
Right.
The first one, yesterday's, we had a beautiful occluded structure.
Mhm.
And I don't know if this one gets there.
Where's the deepest fold? Is it on the southwest side or is it on the east side?
There you go. Let's see. It's right to the south of it, I believe.
You can just bring sea level pressure down to that level and you can kind of see. And then flip it upside down. Yeah, it's like southeast, I think.
Yeah, yeah. Great.
Still like the triple point maybe, or whatever
Mhm.
serves as a triple point in this some way.
Yeah, we could actually, let's add what's your favorite verb, theta or theta E?
Theta E
Let's add theta E to this.
at 800 millivolts.
Yeah. 1.5.
Yeah, right there. And like every 3 degrees or something.
That's actually pretty close to the triple plane.
Yeah, it's
Right.
about what it sort of looks like.
So you can see this really sharp bundle of isotropes, moist isotropes that we characterize where the cold front is. You can see this thermal ridge that's rotating, or that rotates kind of around the cyclone center all the way there toward the center. That's a pretty decent structure.
Yeah,
I'd say.
it does, it looks pretty good. I wonder what it looks like on the vertical, but it looks pretty good in the horizontal. Yeah.
You mean in terms of looking at a theta E surface?
Or just a vertical cross-section through the ridge.
Like this way? Yeah.
No, go back to that prior picture.
Or along the ridges.
Perpendical to its axis, I mean. So, yeah, like that.
Here or further north?
No, just like that, more like that, right through the axis of the ridge.
Okay.
So, north-south?
Yeah, northwest, northeast, southwest.
Northeast.
No, that's along the axis, we want to go perpendicular to it. Yeah, like that.
What we're doing is looking at a cross-section of equivalent potential temperature through this cyclone.
Oh, yeah, look at that, see, it's a little bit weird looking, but it's something like it, it might just be the orientation or something. It's a little bit weird looking. What's the vertical motion look like on that? I'm gonna guess it'll be maximized right in that ridge. Let's see.
Good interval.
Oh, yeah, maybe it has 0 in it or something.
Thanks, Pete, and thanks, John, for the suggestion slicing.
You could be a quarter slice
So we're on the contours are putting a fill pattern of vertical motion in the plane of the cross-section that matches up to the theta E.
So if those W's upward there, where it's,
These are true W's.
the W's would be upward
Positive.
along, are they positive, so they're sinking?
No, they're W, not omega, right?
Oh, they're W, okay, yeah. So that would suggest, since the lines are bending down, but the W is going up, that would suggest diabatic source, which would be lane D.
It's interesting, maybe it's just where the cross-section is taken, but this seems to be right along the,
Yeah, that's a good, that's canonical location for a maximum updraft. That one there is.
but this one's kind of a weird structure further to the east, but maybe this is also some convective. Yeah.
Well, the fact that
Yeah,
theta
mountains,
E,
yeah.
theta E here is increasing with height. So it has to be stable with stratiform cloud.
Yeah, it's forced descent in there. Although that column right there, the middle one, is the least well stratified of all the ones that are adjacent to it,
You know, but it's
as it always is.
still stratiform clouds.
Yeah.
So a lot of times we think of the forcing by convective clouds. But this is actually stratiform clouds, which is causing the effect.
Right. It appears that way for this particular case. So, I want to just be cognizant of time, just a couple things about impacts. We saw waves. What about the total amount of precip that we get with this? Let me share my column list. And so for that, we're going to go to the last. If you're interested in atmospheric rivers and learning more about them, there's you can just do cw3e.ucsd.edu. They have some more information, but there's these localized regions of significant water vapor transport. And for the western United States, they can account for up to nearly a third to a half of their annual precipitation when these come through. And the biggest periods for them are September through March. Let's go to UFS. So this is through a week from today. Total rainfall amounts, this is just to orient ourselves, this is for California, Nevada. We're looking at inches of precipitation, at least as forecast by the GFS. Nearly a foot of rain in the Sierra Nevada mountain range right there. Look at that. That's going to be going to help with the drought. The other question that's often asked is, well, what if this were all snow? Well, we can always do the 10 to 1 thing, but we can go scroll down and take a quick look. Winter weather. This is more for using, we can always multiply by 10 too, I guess. We click on that. And they're looking at, upwards of 79 inches, in some places 80, it's probably gonna be 100 somewhere in there. So that's gonna be a significant event. And if we just go to the end of the forecast period, so this is 384 hours, are they expecting much more than that? Looks like this first burst that they're gonna get is gonna be the big event in the next week, and then the pattern's probably gonna relax back to something that's more common. But if it is gonna be dry and warm there, let's go to the rest of the United States. That probably portends ridge in the west, trough-like structure in the east, which means you're probably gonna get a little bit cooler. This is total accumulated snowfall through the 7th. And there's some snow in our state, perhaps.
Denver's got a big one in there, it looks like, or at least a snowstorm, maybe not big.
So, big event, significant, rain, significant wind. Again, they were talking about 180 knot winds perhaps at the peaks of some of the mountains in the western part of the United States. Some snow, so this is going to certainly alleviate the conditions they've had with drought. So it's all good, but I guess the biggest concern is going to be the debris flows that occur because of lack of plants to soak up sort of water and hold the root system, hold the soil in place, because they've all been burned out or just died because of the dry period, the drought that they've experienced.
So over the next week, we may see some flakes here at the end of that.
Yeah, well, this is for 384 hours, and we just go ahead to 168. Yeah, we're gonna have certainly a cold week, or chilly rain on Sunday evening and Monday.
There's a few flakes up by Baraboo out there.
Yeah, there's some possibilities of, I'm sure John doesn't want to see that. John's like, no snow.
Yeah, that's exciting to me.
And if we go back to the surface map, I want to just finish off the weeks, we do have a few more moments. If there are questions, please ask. Let's just go back to 60 hours where we ended with the MM5. It's a pretty nice looking large scale circulation. So here's that cyclone, kind of looks certainly fall-like, nice cool high to our north, northeasterly winds with the rain coming into the south. It'll certainly feel like fall outside as this cyclone continues to develop and move toward us. We go ahead to 72 hours, which will be Monday morning. Rain continuing, and that's where that snow occurs in the north side of this particular cyclone at the beginning to depart. But
So that's
Monday morning. We've seen snow this early, or even earlier.
Oh, yeah.
It's no big deal. And then this is now Tuesday, or Monday evening, that cyclone heads to the east coast. And note that the rainfall in the west is over. There's some rain and snow in the mountains, but not much in the way of heavy precipitation. Now we're beginning to slowly warm back up.
There's a lake effect there off like here on it, looks like. Quebec.
So, also gives you a nice cold core on October. 120 hours to wind it up. Another cyclone, just looking at west coast storm finally beginning to affect us. Hopefully we have a big warm up with strong warm advection and lots of rainfall just ahead of this next trough. We've been dry, we're going to get our share of rainfall. It's 144 hours for Thursday morning, and then finally Friday morning, maybe go right to weather watch time for next week. This broad cyclonic circulation forecast by the model, that's unusually large. We could actually look at the, just compare that with the 0Z forecast from last night. Didn't like it in the forecast. Not the same.
That looks like a more classical, broad-scale thermal structure
Right.
than the other one does. That's really weird.
Oh, it's just this broad minimum with these cyclones around it, but yeah, that looks more like a typical cyclone. In any case, again, for the weekend, dry, relatively cool until we get to Sunday evening. Then we get some rain into Monday, chilly rain, temperatures in the 40s.
There's still no impressive verticality in there.
No, that's true.
Yep. Still lags. So it was all built up over the Pacific, and then we got these big storms, but it doesn't really carry through to the continental United States.
You get the impression that all this is driven by potential energy of the subtropical jet as opposed to characteristic and potential energy of the overturning process.
Yeah, but the flip side of that is, when we looked at 850 millibar maps on Pete's, so-called super Pete maps, a lot of baroclinicity was close to the surface, but not much in the middle and upper troposphere.
That's right. And that's, I think you need, like I said before, I think the subtropical jets, when they move latitudinally and they get up in toward the Arctic Circle, is when they mobilize the cold air, they lift it up. And once it's mobilized, then you can get very strong polar jets that
Pretty nice of
that
place to-
feed off of that baroclinicity that's at the ground, because they'll pull it up and use it. But right now, if it's laying on the ground, we need something to go up there and lift it.
Or something to bring those isotopes together, some mechanism to bundle
Bring them together, but also lift them off the ground. Something needs some vertical motion, usually you get it from quasi-geostrophic motions that'll forcibly lift it. So it takes a little energy to build it like that.
We'll see when this finally occurs, but maybe some interesting diagnostics to consider, like the circulation of the two hemispheres. Well,
Yeah, that's something you could do. That wouldn't be hard to do. Another thing to do is just keep track of the area at 500 millibars and overlay them on top of each other.
Right.
Because it might well be that early in the season, as the sun goes down at high latitude, it's very easy to produce cold air at the ground, as you're
Right.
pointing out, Greg. But you gotta do something to make that cold get deeper, and one way to do it is to lift the air. And if you don't have a very active regime, then you have a difficulty doing that.
So
It'll be
there's a huge
interesting to
amount of
see.
energy at the ground that's not mobilized. So if you spend some energy to lift the cold versus the warm, then when you release that, you'll get more back than you put in.
Well, it's kinetic
From the
energy
baroclinicity.
transferred into potential energy, yeah.
You transfer it into potential energy, but you also mobilize it so it can be tapped. You can't just have a cold front move from the Arctic Circle down to low latitudes, because friction will stop it. So it just stays up there. But you have to lift it, and then in the absence of friction, you can have these polar operate.
So what's the principle on a synoptic timescale? What would you be looking for, or is it a different timescale?
No, I'm convinced that it's probably related to the polar night jet. But the polar night jet enables the subtropical jets to mobilize the cold air north, and then you get an outbreak of polar jets, because once you mobilize it, then that baroclinicity sets up all these regular baroclinic systems of the winter that'll keep it mobilized. And then if you get a sudden stratospheric warming where you kill the polar jet, polar night jet, then everything
It's over.
is over. And, it can build up again
Right.
if it's early enough in the season, but that's why the polar night, that's why the sudden stratospheric warming has such a profound effect on the winter. Because the winter relies on that polar night jet to leverage everything else.
Well, one way you could tackle it is you could say, what's the equivalent, I think it's 288 Kelvin is the -5 at 850. So you just look for 288 Kelvin at 500 millibars and see what does its seasonal cycle look like? I mean, when does it expand? And is this an unusual time? Is it unusually small right now? And that would indicate a lack of baroclinicity in the middle troposphere. And what is it, what's its variability? I don't know that, but it'd be an easy problem to mount anyway, an easy attack to mount. That's kind of interesting.
Well, thank you, Pete, for driving. Thank you, Greg, and thank you, John, for your input on this.
Oh, yeah,
Impressive
thanks, it was a
storm.
great presentation. Yeah, great.
Yeah.